When the Francis Scott Key Bridge collapsed in March 2024, the internet was flooded with conspiracy theories. But to a physicist, the culprit was much simpler and much more terrifying. It wasn't a structural failure, it was a math problem. Specifically, the formula for kinetic energy. When you take a ship weighing 100,000 tons and move it at just 8 knots, you are not creating a vehicle, you are creating a missile. Welcome to Failure Point. Today, we calculate exactly why no bridge on Earth could have survived the Dali. To understand this disaster, we have to talk about scale. The Key Bridge was built in 1977. Back then, the largest container ships carried about 2,000 containers. The MV Dali, the ship that struck the bridge, can carry 10,000. Modern megaships are essentially skyscrapers floating on their sides. The Dali weighs roughly 110,000 tons fully loaded. Even drifting at a slow speed, the momentum is astronomical. In the equation for kinetic energy, velocity is usually the main driver, but here, mass is king. The force delivered to that bridge pier was roughly 100 million newtons. Bridges are usually protected by dolphins, those concrete bumpers you see sitting in the water. Their job is to sacrifice themselves, crumbling to absorb the impact. But the Key Bridge's dolphins were designed for 1970s ships. Against the Dali, they were effectively cardboard. The ship plowed through the protection systems without even slowing down. This exposed the bridge's fatal flaw. The Key Bridge was a continuous truss. This means the entire main span is one single, connected skeleton. It's efficient, but it lacks redundancy. When the Dali took out the southwest pier, the physics were instantaneous. The bridge lost its primary leg. Because the truss was continuous, the failure didn't stop at the break, it traveled. The top part of the bridge, which is normally under compression, was suddenly subjected to massive tension forces it was never designed to handle. It snapped like a dry twig. In seconds, the entire structure effectively seesawed into the water. This wasn't bad engineering. In fact, the bridge held up exactly as the math predicted it would. It just never stood a chance against the energy involved. So, how do we fix this? We build islands. Modern bridges use massive rock islands to ground ships before they ever get close to the concrete. I'm an engineer, and this has been a Failure Point analysis. Subscribe for more engineering.